Okay, hello everybody. Good morning, all of you. We start with today's small quote. Forget the mistake, but remember the lesson. Okay, always there is no point in regretting or worrying about something already happened. Okay, and it's natural that mistakes people do, and everybody does it. So it doesn't matter, but you have to forget about the mistake. Don't regret about it, but remember the lesson. That is, we should not repeat the mistake. And today is the birthday of John Glover. So he developed the Glover Tower in 1859 to reclaim useful chemicals during the manufacture of sulfuric acid, the most important industrial chemical. So the previous lead chamber method used sulfur dioxide, a nitrate, air, and water, but lost the nitrate in the form of nitric oxide to the atmosphere. This was expensive since the replacement of nitrate had to be imported from China. And Glover introduced a mass transfer tower to recover some of this lost nitrate. In each tower, sulfuric acid, still containing nitrates, was trickled downward against upward flowing burner gases. The flowing gas absorbed some of the previously lost nitric oxide. By recycling these gases into the lead chamber, the nitric oxide was reused. He did not patent the process, but gave it freely to benefit the industry. So that is one of the great thing about him. So many people that were mainly in foreign countries, they try to cash everything, every idea, but only there are few people who leave it to the benefit of the society. Okay, today we start parabolic solvers, and before going to this, we will see what we have done in the last class. So in the last class, we have revised the all elliptic solvers like Jacobi method, point Gauss seidel, point successive auto relaxation, line Gauss seidel, line successive auto relaxation, alternating direction implicit, alternating direction with or relaxation like that. And we have seen what is how the coding is done. So coding of all the elliptic solvers and study of the effect of relaxation factor that we have seen. If you change the relaxation factor, how it happens and how the number of iterations get affected and how we get the optimum relaxation factor like that. Okay. So then method of using PDE tool we have seen in MATLAB to solve partial differential equations. We have seen a simple tool where you can solve any elliptic, parabolic, and hyperbolic generalized equations, right? And it's complete Navier-Stokes equation. It may not be able to do that, but most of the things it will cover, and very simple way. And that also this is for regular geometries, right? Like rectangle, ellipse, like that, circle, ellipse, like that. It can solve, but not for any other things. Okay, but the tool is very useful. And solution of Laplace's equation for temperature on rectangular geometry with both the Dirichlet condition and Newman conditions we have seen, and study of the effect of boundary conditions on isotherms. So we have seen how if one is insulated, how the contours will change. If I have changed two Dirichlet conditions on two boundaries, how it changes. Like that we have seen for different types of boundary conditions, how the contours will change, how the solution will change. Okay, these are the things we have seen. Today we will see the parabolic solvers. So we have seen the simple model equation. So I can have energy equation of the sort like, so this is unsteady term and this is the diffusion term. So this is unsteady, one-dimensional heat conduction equation. Without heat generation. Okay, this is the way we get that. And in the same way, If I take the momentum equation, so we have like dou v by dou t. Yes. Okay, this is the generalized equation I have. If I have unsteady 1D without okay, plus this also will be there without pressure and body forces. So if I have like this, so for this I will have dou u by dou t only because it is 1D. And okay, and even convection term also negligible. So this is also not there, this is not there, this is not there. In this one dimension means mu dou square u by dou x square ut is equal to mu ux. Like this, we have the parabolic equation. These are parabolic equations. So as I told, if I write program for coding for one of the equation, just to change the temperature to velocity, you can solve the momentum equation. The coding will be same because the equations are same. Okay, one more thing I wanted to tell here. So here Tt is equal to alpha Tx. So this is unsteady equation. If I have steady 1D heat conduction equation, so that is only Txx equal to 0. Dou square t by dou x square equal to 0. Or if I take 2D equation, alpha into Txx plus Ty. And here also Txx plus Ty equal to 0. And we know that this is elliptic. This we have already solved. Okay. And the same problem, steady problem, can be solved by this also. Right? So if I can give the initial solution and do time marching till you get the steady state, then once you get the steady state, this solution of this equation and this equation will become same. Am I clear?
Yes, sir.
So the advantage, so many times, okay, people feel that, okay, this is a easier one. I don't have one dependent variable, right? So the equation is less complicated compared to the parabolic equation, like that people may think. But many times people prefer to solve the parabolic solver using time marching. Okay, what is the advantage? Okay, what is the advantage? Here also, we are both are iterative methods only. But in elliptic solver, intermediate solutions will not have any physical significance. But if I take this, if at t equal to 0 or at t equal to some time, I have the initial distribution. And if I do the time marching, right? So the intermediate values also, that is after 1 minute, what is the temperature distribution? After 2 minutes, what is the temperature distribution? I can see the evolution of temperature distribution. Suppose if you are doing a heat transfer experiment, right? And what you are doing till steady state, you are going to the equipment after every 5 minutes, you are noting down the readings. And till it may take 1 hour or 2 hours to get it steady state. So all the intermediate solutions, they have significance, right? All those I can get from this particular parabolic solver. Am I clear about it?
Yes, sir.
So both gives me steady state solution, but I can have the time history by solving non-steady unsteady equations. Okay, that is one of the advantages. Same solution I will get finally, but if you do the time marching by solving the parabolic equation, I will get the physical, because you can understand whether it is going properly or not. All right. So intermediate solutions, if you see, okay, it is physically meaningful solutions I am getting, so I am doing it right way. Okay, so that idea you will have. Okay, so this I wanted to compare these two. So next, coming to 1D, we will see different schemes. Okay, so here time, because it is one-way coordinate, I have to take one-sided difference only, because the present depends on the past. Okay, so I will have either forward difference or backward difference. And this is diffusion term. Diffusion term, I always told it has elliptic nature. That is, it the information goes uniformly in all directions. So central difference is preferred here. So naturally, what we try to have is forward time and central space. And we will see first simple things like explicit scheme. FTCS explicit scheme. So what I do is I will discretize this at point I and at time n. Okay, so it is a 1D, so it is like a fin. I will divide this into number of points. So I plus 1, I minus 1, I plus 1, I plus 2, I minus 2, like that I have. And I may have some n points or n plus 1 points and n intervals. Okay, so in any way, or n interior points and n plus 2 total points. Based on whichever is convenient, you can name them in that way. Okay, so I have this way. And then how to write this discretized equation. This Ti, forward time means Ti n plus 1 minus Ti n. Okay, so this is forward difference by delta T is equal to alpha central difference for Txx, that is alpha dou square T by dou x square. So I will have Ti plus 1 minus 2 Ti plus Ti minus 1 by delta x whole square. And these are at n. So all the old values. Okay, I use the old values. And so how many unknowns are there? Only one, Ti n plus 1. So what I will rewrite this as Ti n plus 1 is equal to Tin plus alpha delta T by delta x whole square into Ti plus 1 minus 2 Ti plus Ti minus 1. Okay, this alpha delta T by delta x square, this is called as diffusion number. Diffusion number. Okay. So I'll how I write it is Tin plus 1 is equal to Tin plus D into Ti plus 1 minus 2 Tin plus Ti minus 1. Okay, so this is the equation. So if I want like a program code I have shown for elliptic solver, for the parabolic solver you will write like this. A new value is calculated using old values. Okay, if I know the, and I do a for loop from 1 to n. Okay, if there are n plus 2 points, I can maybe okay, if it is some 1 2 3 4 etc. So 2 to n minus 1, I can write the if n points are there, I have to calculate 2 to n minus 1. I have to give a loop for I equal to 2 to n minus 1, and I have to write this equation. That's all. It goes in a loop, it calculates all the values and at a particular time. And for using these values, if I calculate the next one, so after 2 delta T, I will know the values. Then use that as the old values and calculate. Like that, I can get the new values, and I will always check the convergence. So error will be T nu, that is tin plus 1 minus tin. This is the error. And if I take sigma, I will take like this. It should be less than some epsilon. So in that way, I can write the code. So if you see the order of accuracy, because this is single side forward difference or backward difference, it is first order accuracy delta t, and central difference txx, it is delta x whole square. Okay, this is the order of accuracy. And coming to stability, so some statements I will give now, later I will prove that. Okay, now in the next class or maybe the next class, when I talk about the stability, I will prove whatever statements I give now. Okay, about stability, as I told in the last class, all explicit schemes are usually conditionally stable. They are conditionally stable. So I'm going to prove that they are stable. And what is that condition? D less than or equal to half. This is condition for stability. Okay, so that is so D means alpha delta T by delta X whole square should be less than or equal to half. So once I decide the grid, okay, how many points I want to do. So delta T should be less than or equal to delta X whole square by 2 alpha. So when you take delta T, when you choose delta T for doing the time marching, so it should not be greater than this. It should be less than this delta X whole square by 2 alpha. So this is very, very important. Many times people ignore it. What I do is, okay, I'll take some grid and I use some delta T. It is working. So as I told initially, what we do, we take a coarse grid because number of points will be less, and I want to see whether it is working or not. Once it is working, then my scheme is working. So what I do, I refine the grid so that I will get better accuracy. So that's what people do. Many times, many people, what they do, the mistake is they refine the grid and execute it, and it will not work. It will become unstable. They will not understand it is working previously for the previous data it worked and why it is giving problem. So they will forget about the stability condition. So when delta x is reduced, because delta x is very small and delta t should be reduced very much, delta x whole square, right here on the right side. So delta t should be reduced very much. So for steady state, it takes very large number of iterations. Suppose if I taken delta x is 0.1, I will have some delta t. And if I reduce the delta x to 0.01, you can see delta t, how much it is to be reduced. Okay, it should be reduced very much. So what will happen, suppose it takes 1 hour, like heat transfer experiment only. For that, you have written the code. Okay, so suppose t is equal to 0.001 seconds or something like this. Okay, if delta t is this. And if it is to be obtained after 1 hour, what is the solution? Okay, so 360 seconds. So 360 seconds means how many time steps I have to make? So 360,000. Okay, so many time steps, millions of time steps I have to take many times. Am I clear about it?
Yes, sir.
Okay, so that is the main limitation and explicit thing. But the program is very, very simple. As I told in the thing, only this equation is to be solved. Okay, nothing else, just one line, and the program will be very, very small. Okay, next we will go to the next point. Okay, once this has worked, so naturally people try to uh, upgrade the schemes. Okay, so FTCS has worked. It is first order accuracy in time and second order accuracy in space. So why not I have second order accuracy both in time and space? Okay, like that Richardson has tried. So this is called as Richardson scheme, and this is CTCS scheme. Central time, central space. So I have TT is equal to alpha EXX. It is discretized at I and N. Okay, so at the nth time, if I want central difference for this, central difference gives me second order accuracy. So at n means I have to take the ti n plus 1 minus ti n minus 1 by 2 delta t. Central difference for the first order derivative. What I do, I take old value and new value. And one more thing also, okay, I will tell you later. Okay, for the explicit, so if I take this is time at n plus 1, n plus 2 like that. This is I plus 1, I plus 2, sorry, I plus 2, I minus 1, I minus 2. So we have written the equation as Ti n plus 1. This is equal to, it is using Ti minus 1, Ti, Ti plus 1. These values, these old values, it is using. At nth time, this is using this value, this value, this value to calculate, and this value also. These three values are used to calculate this value. So it is like if a parent is there in a person is there in the hostels, right? If you want to know how he is doing there, okay, so normally what he will do is he will see what are his neighbors. Okay, so yesterday what is his neighbor, this side and this side, and what is his behavior, and now based on that he will predict what he will be today. Okay, based on the past behavior of him and his neighbors, his present behavior depends. So that is the way it is predicted. Okay, so in the same way, okay, the old values of its value, its neighboring values decides about this value. This is FTCX explicit. And coming to Richardson scheme, Ti n plus 1 minus Ti n minus 1 by delta t is equal to alpha Ti plus 1 n. This is same Ti n plus Ti minus 1 n, like this, by delta x. Okay, this is the way it is done. So this is the order of accuracy is second order in time and second order in space. Okay, I will not discuss about this much because the stability when they checked, this is found to be unconditionally unstable. Okay, many times we try to expect that it will do a better thing, but unfortunately, sometimes it may not work. Our logic fails many times. So this is what happened. They found that it is unconditionally unstable. Okay, so this didn't work. So when this didn't work, but still some people are interested in second order in time and space. Okay, so again people have tried. Okay, so two people have tried, like Dufort and Frankel. So they have modified FTCS, the CTCS. Okay, what they have done is, again, Tt is equal to 1 for Txx. So they have taken central difference only, Ti n plus 1 minus Ti n minus 1 by 2 delta t is equal to alpha into this Txx Ti plus 1n minus 2Tin will be there, isn't it? 2Tin. 2Tin, that is the value of the present value of a point at a point. They have taken it as the average of past and future values. Average of past and future values. It is like Ti n plus 1, that is future value, minus past value. Average of these two. Like this they have taken. And plus Ti minus 1. Okay, this is the way they have modified. and okay, whole by delta x also, like this. Okay, if I rewrite it, I will get this is equal to this 2 delta t I will take to the other side, tin plus 1 minus tin minus 1 is equal to 2d into ti plus 1n minus 2tin plus 1 plus 2tin minus 1 plus ti minus 1n. Like this I will get. But here I have unknown tin plus 1 on the right side and also left side. tin old value only, tin minus 1 also old value only, but tin plus 1 is the value. This is the only one unknown, but it is there on both sides. So bring it to the left hand side. So what will I get? 1 plus 2d tin plus 1 is equal to 1 minus 2d tin minus 1. 1, is it 1 plus 2d only? This that goes that side. Tin minus 1 comes this side. And plus 2d into ti plus 1n minus ti minus 1. Okay, something like that you will get. And so this is the way he got it. And so if you see the order of accuracy, it is second order in time and second order in space. Okay, but when they do the consistency analysis, there are two things: consistency analysis and stability analysis. So when they do the consistency analysis, they found that not only these two, there is one more condition to be satisfied. Delta t by delta x whole square also should tend to 0. So delta t tend to 0, delta x tend to 0, and delta t by delta x whole square also when they tend to 0, then only this will become the original partial differential equation. So they found that. So this is another condition to be satisfied. And coming to stability, they found that it is an exceptional case, right? It is very exception. It is found that it is unconditionally stable. Normally, all explicit schemes, this is explicit scheme because only one unknown. All explicit schemes usually, right, anytime it will be conditionally stable, but this is the only particular scheme which is unconditionally stable.
Hello, sir.
Yes.
The coefficient of tin minus 1 is 1 plus
1
4d,
plus 2d, right? 1 plus 2d, right?
1 plus 4d.
No, 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 no. No, no,
So
no, no. It
tin plus 1 is
no, no,
talking about.
it's 2 only. No, no. Here, this 2 gets cancelled. I think there is no 2 here. There is no 2.
Yes, sir.
Right. So it will be 1 plus 2d only. Okay. So this is found to be unconditionally stable. This is one particular exception. Okay.
Sir,
Now,
what do
yes.
we refer when we say it's conditionally stable or unconditionally stable,
Uh,
sir?
that is, if it is to be stable, I have to satisfy some condition. Like FTCS, the condition is d less than or equal to half is the condition to make the scheme to be stable.
Okay, sir. Okay, sir. Got it.
Okay,
Thank you.
here it will be stable for whatever delta t you take.
Yes, sir.
Okay, and so here the order of accuracy is increased and we got unconditionally stable. So this seems to be very, very good. But there is one problem here. Can anybody tell me what problem? I will get it from the equation. Okay, to solve tin plus 1, I need old values of 2 iterations. This is at nth iteration, this is n minus 1th iteration. At time steps, previous 2 time steps, I should have the values to calculate the new time step value. Am I clear?
Yes, sir.
So this is called as 3 time level scheme. Okay, what's the problem then? So when I want to start with the iteration, okay, I have initialized the values at n. I want to calculate at n plus 1. I have values at n only. How can I have values at n minus 1? Is it clear?
Yes, sir.
So it is not a self-starting scheme. For first time step, some other scheme is to be used. Okay, some other scheme is to be used. Okay, take and the iteration values, that is at 0 iteration. You calculate first time step using some scheme like FTCS scheme. And once you have two values, then you go for Buford-Frankel scheme. And then you go on, because always you will have two old values. So it's not a self-starter, and it needs a help of some other scheme. And so because of this, what happens is the accuracy gets affected by the starter scheme. Okay, so unless I use second order accurate scheme, if I use first order accurate scheme for first time step only, it loses its second order accuracy. So that is one thing. And another thing is it needs more storage, because it has to store all values at two time steps. Okay, if there are a million of grid points are there, I have to store all the values of two time steps to calculate the new time step value. So these are the problems. Though it seems to be okay, it is second order accurate, unconditionally stable and all. These are the limitations for this. Is it clear?
Yes, sir.
Okay, then we go for what are called as implicit schemes. So we have discussed about three schemes: FTCS, which is first order in time and second order in space, and it is conditionally stable for d less than or equal to half. Then we discussed Richardson scheme, which is CTCS scheme, and which is of second order in time and second order in space, but it is unconditionally unstable, which cannot be used. Then the third scheme we have discussed is Dufort-Frankel scheme, which is modified CTCS scheme. There, the right-hand side, UIN, is replaced by the average of past and future values, like half into UIN plus 1 plus UIN minus 1. So that is the way we got Dufort-Frankel explicit scheme, which is second order in time and second order in space. But there is one more condition to be satisfied, like delta t by delta x whole square also should tend to 0. And the second one is it is unconditionally stable, but its limitations are it is not a self-starter, and some other scheme is to be used for starting, which affects the accuracy, and it needs more storage space. Okay, so that is the things we have discussed. Now coming to implicit schemes, T is equal to alpha Txx. And in implicit schemes, I discretize at I and at a time n plus 1. I take n plus 1. And here, when I take the discretization of this particular one, I take backward difference. Backward difference means I take n plus 1, I take the previous value. This is something interesting. Tin plus 1 minus tin by delta t. I write the same thing, but now I say backward difference. And previously I write the same thing, I am telling it is forward difference. Because there I am discretizing at n, and now I am discretizing at n plus 1. Expression is same, but I say there it is forward difference and here backward difference. And so we will see BTCS implicit scheme. Backward time and central space. So right hand side will not change. ti plus 1 minus 2ti plus ti minus 1. But these things, because I am doing at n plus 1, I have to take n plus 1. Okay. And okay, the previous one, actually, I wanted to draw that points. So this is like if I take this way, and this is n minus 1, n plus 1 if I take. And so it is using ti n minus 1 and ti minus 1n and ti plus 1n. So this it is using, this it is using, this it is using, this it is using to calculate this value. So interestingly, to calculate this value, its old value is not used. Okay, so this is the way it is done. Okay, in implicit scheme, what it will do like this by delta x whole square. So ti n plus 1 minus ti n is equal to d into ti plus 1 n plus 1 minus 2 ti n plus 1 plus ti minus 1. So here, how many unknowns are there? All values at n plus 1 are unknowns. So there are more number of unknowns. How many unknowns? tin plus 1, ti minus 1 n plus 1, ti plus 1 n plus 1. There are 3 unknowns. So if I bring the unknowns this side, so I will get, okay, I will take to that side. D ti minus 1 n plus 1 and minus 1 minus 2d. We can take any way, right? This way I am writing. So here these are the 3 unknowns. So this which results in tridiagonal matrix. Okay, so I have to use tridiagonal matrix algorithm or Thomas algorithm to solve it. And so the diagonal elements, diagonal is 1 plus 2d, upper diagonal d, lower diagonal d. So some of the non-diagonal terms is d plus d 2d, and diagonal term is 1 plus 2d, which is more than that. Okay, so aia is equal to sigma ia is greater than, because this is 2d and this is 1 plus 2d. Okay, so there is diagonal dominance. And so here, if you see order of accuracy, again first order in time and second order in space. And because this is implicit, so stability, this is unconditionally stable. This is unconditionally stable. So this is also called as Lawson method. BTCS implicit is also called as Lawson scheme. Usually we give respect to the people who come out with the schemes. So instead of giving BTCS, we give the name of the person who came with this. So Lawson scheme. So this is the way we have to solve it. So this is first order in time and second order in space. Okay, we have to use the Thomas algorithm. And again, people try. And if I want to have second order in time and space, so is there any method? So people have again tried and tried. And so here, if I take this again like this, So to calculate, this is n plus 1, this is I minus 1, I plus 1. So it is to calculate this value, what it is using is its old value here and new value of the neighboring points. Okay, so what he is previously and what his neighbors are now, based on that his behavior depends like that. Okay, ti plus 1 and plus 1, ti minus 1 and plus 1, it depends on that, and ti n. Okay, so this is the BTCS implicit or Lassonен. So now there are two people again, like Crank and Nicholson. So this is Crank-Nicholson scheme. We call this as Crank-Nicholson semi-implicit scheme. So what he has done is, he has taken, he has taken this at I and n plus half, at n plus half. And he tried CTCS only. He tried CTCS, central time and central space. So at n plus half, if I want central, so it is like this is n plus half, this is n plus 1. This is I minus 1, I plus 1. So at this point, I want to calculate or I want to do the discretization at this point. So what I do is, if I want to have time derivative as central difference of time, so I will write this as ti n plus 1 minus ti n by delta t. So this is these two neighbors I am taking the central difference. So this is again interesting. You see, I'm writing the same expression, tin plus 1 and t minus tin by delta t, but I say this is central difference because I am writing at time n plus half. So at time n plus half, I am taking both sides. One is n and another is n plus 1. Am I clear about it?
Yes, sir.
And here alpha, and I take this as average of this central difference of space at n and n plus 1. So I will take ti plus 1 minus 2 ti plus ti minus 1 by delta x whole square. This I will take it n plus 1 plus tin plus 1 minus 2 ti plus ti minus 1 by delta x whole square. This I will take it n. Central difference at n plus 1 and central difference at n I am taking the average of these two so that I will get the central difference at n plus half. Am I clear about this?
Yes, sir. And tin plus 1 minus tin by 2 delta t, no, sir?
No, it's not 2 delta t. What is the distance between n and n plus 1?
Delta t.
Delta t only. If I take ti n plus 1 minus ti n minus 1, then that is 2 delta t because the distance between them is 2 delta t. Is it clear?
Yes, sir.
Okay, like that. So I can write this again. So here also, again, the unknowns are ti minus 1 n plus 1, ti n plus 1, and ti minus 1 n plus 1. So I have to rewrite them. And so suppose I write this ti n plus 1 minus ti n is equal to d by 2 into ti plus 1 minus 2 by ti plus ti minus 1 n plus 1 n plus 1 n plus 1 plus ti plus 1 minus 2 ti plus ti minus 1 n. Okay, like this. So again, I can bring the n plus 1 things this side, and the tin I can take this side, so that I will get 3 unknowns this side, and all the known values. These are all known values. So this will become, this needs tridiagonal matrix algorithm. Okay. And the order of accuracy, central time, that is delta t whole square and delta x whole square. And because this is implicit, this is unconditionally stable. Is this clear? So it
Yes.
is
Sir, you said it's implicit, so it's unconditionally stable. So, sir, like,
implicit is unconditionally stable.
so like all implicit schemes will be unconditionally
All
stable.
implicit methods are unconditionally stable.
Sir, what can be the reason behind this?
I will prove it, right? Later,
Okay.
when I talk about stability, I will prove it.
Okay, sir. Thank you.
Okay, right. And here, to generalize this Crank-Nicolson scheme, okay, they came with a scheme what is called as beta formulation. So here, what they have done is they have taken the average of new values and the old values. Okay, giving weightage for the old values 50% and new values 50%. So instead of this, I should be able to give different weightages also. So what can be done is, I will write tin plus 1 minus tin by delta t on the left side as it is. And here, d into, they have done like this, beta into ti plus 1 minus 2 ti plus ti minus 1 n plus 1 n plus 1 n plus 1, okay, plus 1 minus beta into ti plus 1 minus 2 ti plus ti minus 1 n. Okay, so beta is the weightage factor. So I can change the weightage to be given. So if you see this equation, just so if you see this equation, if beta equal to 0, what happens? This becomes 0. There is no more implicit thing. Only this one only will be given. So only tin plus 1 is the unknown. All others are known values. And this becomes FTCS explicit scheme. If beta equal to 0. Similarly, if beta equal to 1, so this term will go off and only this term will be there. And I will have what is called as BTCS implicit or Larson scheme. If beta equal to 0.5, right? So this is half and this is half, and it will become d by 2 into this. It will become Crank-Nicolson scheme. Is it clear?
Yes, sir.
I can, if I want to change the weightage that is to be given to this and that, so I can change it. Only thing is the stability is the problem. If I take beta equal to 0, this will become conditionally stable. And beta equal to 0.5 and 1, they will be unconditionally stable. Okay, so that I have to keep in mind. So I have to see what weightage I have to give. If I give the weightage less than 0.5, it is going to be unstable or conditionally stable. Okay, so that I have to be clear. And so I can show one problem that is solved. Okay, all these things will be there. Okay, this is the problem, example problem. It is solved. Dou u by dou t is equal to nu dou square u by dou y square. Okay, the new value is given. It is 0.000217 meters square per second. Okay, that is kinematic viscosity. And so here there are two plates. Between this, there is some fluid. Okay, so one of the plate is moved by some velocity. Okay, and because of viscosity, what happens? Gradually, the next layers adjacent to the lower plate gets velocity. And after some time, if you march in time, gradually the next layer moves, and finally it comes to a straight line variation. Okay, that is the way it happens. So I want to find out, okay, how this velocity distribution between lower plate and the upper plate. Okay, the height is given to be 40 mm, and the velocity of the lower plate is given to be 40 meter per second, and t equal to 1.08 seconds. After 1.08 seconds, what is the distribution I have to find out? Okay, so that is that it is asked. So initial condition, everywhere the velocities are 0, and t greater than or equal to 0, this plate at y equal to 0, it is u equal to u naught, and this is stationary, so u equal to 0 at y is equal to h. Okay, this is the way it is given. So I have to take this height, okay, 40 mm, and I have to discretize it, divide into number of points, and I give the values u velocity to be 0 everywhere. Okay, so that is the initial condition. Then after each point, I have to choose the delta t, because delta x is fixed. Suppose 40 mm, I take 1 mm gap between the nodes. Okay, so I am going to have 41 nodes, and delta x is 0.001 meters. Okay, so based on that, I have to calculate what delta t is to be chosen. Because alpha delta t by delta x square is less than or equal to half, I have to choose delta t based on that. And I have to march in time till it reaches 1.08 seconds. So I can calculate how many time steps it needs. Okay, it is given. I have to calculate like this. I have to do FTCS method, and delta t equal to 0.002 seconds. If I take like this, okay, so the number of time steps will be 541 to get 1.08 seconds. And if I take this way, I will have d less than or equal to half if I calculate. But if I take a little bit more, 0.00232 seconds, and if I calculate alpha delta t by delta x whole square, it is going to be a little bit more than 0.5. And I will show you later that it becomes unstable. And similarly, you are asked to calculate Buford-Frankel with the different time steps, and Larsson with different time steps, Crank-Nicholson with different time steps. So if I do like that, I'm going to get this way. So initially, everywhere it is 0 velocities. And after few time steps, I'm going to get the velocity distribution this way. After few time steps, because the upper layers gets accelerated and all, so gradually it will become like this, and finally it is 1.08. If I go to further time steps, finally it is going to become a straight line. Okay, so that is the way. If d is equal less than 0.5, if I take 0.002, then it is less than d is equal to 0.434. That's why I'm getting a stable solution. But if I take 0.00232, then d equal to greater than 0.5, 0.50344. You can see that as time steps go forward, it is going to oscillate. This is what is called as instability. Okay, analytical solution is this. I can always compare, because analytical solution, this is a simple equation. Mathematics people already have solved it. And so this is the equation. And I can find out what is the error. And so comparison of error distribution for various schemes at t equal to 1 point. If I use FTCS, Buford-Frankel, Larsson, and Crank-Nicholson, I can find out what are the errors at different points. So this is the way I'm going to get the errors. And okay, so that is the way. So next class, I will discuss about the 2D parabolic equation. So if I take in this way, so what is the way I have to go about? Okay, that we will do in the next class. Any questions? Any questions?
No, sir.
Okay. Okay, we will go for the story then.
Yes, sir.
Yes, sir.
Okay, so some 2-3 small real stories. Okay, one thing. First thing is his name is synonymous with intelligence. Yet it wasn't always that way for him. As a child, he didn't start speaking until he was 4. Till 4 years, he didn't speak, he couldn't speak. And he couldn't read until he was 7 and was thought to be mentally handicapped. Do you know who he is?
Einstein.
Yeah, he's all. He went on to win a Nobel Prize and altered the world's approach to physics. I guess he was just thinking of the right thing to say for those first 4 years. And he's Einstein. So he says, weak people revenge, strong people forgive, and intelligent people ignore. So there is another. He has missed more than 9,000 shots in his basketball career. He has lost almost 300 games. On 26 occasions, he has been entrusted to take the game winning shot and he missed. He has failed over and over and over again in the life. And that is why he became successful. He became very great. And basketball means anybody who is interested in basketball will know his name. And he is Michael Jordan. And he says, obstacles don't have to stop you. If you run into a wall, don't turn around and give up. Figure out how to climb it, go through it, or work around it. He says, I can accept failure. Everyone fails at something, but I can't accept not trying. Okay, so you can see nobody gets always successful or nobody get things easier, right? So here, Jordan's individual accolades and accomplishments, six, sorry. Okay, most valuable player awards, 10 scoring titles, 5 MVP awards, 10 All NBA first team designations, 9 All Defensive first team honors, 14 NBA All Star game selections, 3 All Star game MVP awards, 3 steal titles, and 1988 NBA Defensive Player of the Year award. And he holds the NBA records for career regular season, scoring average 30.12 points per game, and career playoff scoring average 33.45 points per game. So you can see his accomplishments, but if you see his real thing, right, you cannot imagine that he'll become like that. Okay, so that's interesting thing. And third story, it everybody knows when he was a child, his teachers called his parents regularly and tell them that their child is weak and can never succeed in life. His teachers were convinced that teaching a brain as slow as his is a waste of time. He failed in his experiment 10,000 times to obtain a solution. Who he is?
Addition.
Yeah, Thomas Alva Edison. Right? So he is guided by mother only. And he says, I have not failed. I have just found 10,000 ways that won't work. So that is the spirit. Our greatest weakness lies in giving up. The most certain way to succeed is always to try just one more time. That's why you could do such experiments. So he mainly for filament, he has tried 10,000 ways of finding out the material for the element, and finally he succeeded. Okay, thank you very much. Thank you. See you again.
Thank you, sir.
Thank
Thank
you.
you, sir.
Sir,
Yes.
you did not share those MATLAB codes, sir.
Yeah, yeah, I will send it. I forgot.
Okay, sir. Thank you, sir.
Yeah. I will send the elliptic code and also that tridiagonal code also, because unless that is there, this will not work. Implicit,
Yes, sir.
right? Both codes I will send.
Okay, sir.
Okay, right.